So welcome to continuation after the coffee break. Our next talk is titled IPv6 DualStack in Kubernetes, why, when, where, and how. And I will introduce you Rastislav Szabo. It's all yours.
Thank you. Thanks for introduction and thanks for organizing such a nice conference. Yeah, so this talk will be a bit about networking, a little bit deeper into networking, about IPv6 and DualStack in Kubernetes. But before going into that, let me introduce myself. My name is Rastislav Szabo. At the moment, I'm working as a software engineer at Isovalent, the company behind Cilium. It's quite new. I'm still a newbie there. But even before Isovalent, I had a privilege to work on many nice open source projects, such as Kubernetes platform, some other projects around Kubernetes, and in the past, some projects, open source projects around software-defined networking. I'm based in Banská Bystrica, Slovakia, and when I'm not working, I'm also a dad of 3-year-old boy, and I enjoy the time spent together with my family. And occasionally, I'm also an orienteering athlete or orienteering race organizer. So what's today's agenda? I would like to start with some introduction of IPv6 and why we need it. Then I would introduce DualStack networking. I'll show you how IPv6 and DualStack works in Kubernetes and how it can be enabled. And at the end of my presentation, I would go through some most common cloud platforms and talk about IPv6 and DualStack support across the cloud providers. And if we still have time, we can do some very short demo of DualStack with Cilium CNI. So before going to IPv6, let me start with IPv4. IPv4 is the core networking protocol of the internet still. It was standardized back in 1991, so like 40 years ago. And in basic words, it is used to transfer pieces of data that we call packets over the internet. And each packet contains sender and receiver address that we call IP address. And this IP address in IPv4 is a 32-bit integer value. And that's actually the problem of the IPv4 protocol. 2 to the power of 32 is only about 4 billion addresses, which is less than the current world population, which means that not everybody on this earth can have their own IPv4 address. And due to the lack of IPv4 addresses, they are almost unavailable in certain regions, like Asian and Pacific regions, and they are in general becoming very expensive resource. The workaround that we have applied to get to work around this IP address exhaustion issue is called network address translation, using which we can hide multiple hosts behind single IP address, but it brings some complexity and many limitations. So the next or the real solution of the IP address, small IP address space problem is the IPv6 protocol, which is actually pretty old as well. It was drafted in December 1998. And the biggest benefit of it is that it provides a larger address space. So the IPv6 address is 128-bit integer value, which give us this amount of possible IP addresses, which is actually enough to address every single atom of the planet Earth. We use hexadecimal notation for IPv6 addresses, 8 groups of 16 bits each, separated by colons. You can see some examples there. Those two starting with 2001 are equivalent. And bed colon, cafe, 2 colons is also an IPv6 address. Thanks to this large address space, we do not need network address translation anymore, at least not because of lack of the addresses. One good benefit of IPv6 is that IPv4 can be transported or tunneled via IPv6 networks. And thanks to that, it was adapted quite early by telco and ISPs internally, especially in mobile networks. So many current internet users, even if they use IPv4, they don't even know that their packets actually traverse some part of their path via IPv6 network. What are some other benefits of IPv6 apart from the larger address space? First, it is more efficient routing, mainly because there is no need for network address translation, which itself requires a lot of processing. But also, there is, for example, no checksum calculation on each hop. IP fragmentation is not allowed by design. Another benefit is built-in security features, such as IPsec, which was natively incorporated during the design of IPv6. And the fact that each endpoint in the internet can have their own IPv6 address means that we have end-to-end transparency across the whole network. So we can see at every single point of the network who is the originator and who is the destination of that packet. That is actually also an anti-security feature. Since we can have public IPs anywhere, it means that we may need more firewall rules. Apart from this, there are many other features like stateless address auto-configuration, which can replace DHCP, address mobility, so you can travel with your public IPv6 address across the globe. Extension headers, that's a mechanism that can be used to extend IPv6 to various different use cases. One of them, for example, being SRv6, and that's the one that I wanted to show you. It's quite complex stuff, but I just want to show you what's possible with IPv6, also with connection to Kubernetes. So segment routing for IPv6 is a network programming framework built on IPv6, which leverages source routing paradigm. Source routing means that whole path of the packet is encoded at the source of the segment routing domain. And what we call packet processing program is essentially a sequence of instructions that can be part of the IPv6 header or IPv6 extension header that we call segment routing header. And through that, we can do some clever things like traffic engineering. We can, for example, tell our packet to traverse some optimized low latency path through ISP network towards the other branch of your company. We can do VPNs, network service function chaining, etc. And everything natively via any IPv6 network. If you are interested more in segment routing, I would recommend KubeCon NA 2022 talk by Daniel Bernier from Bell Canada and my colleague Luis de los Santos from Isovalent. It's very interesting. But let me go back to IPv6 and IPv4. So as it turned out, we cannot just turn off IPv4 in our internet and start using IPv6 at a single point of time. So we need some meaningful transition strategy. And that transition strategy is DualStack. DualStack actually means that DualStack-enabled devices can support both protocols at the same time, so that they can have both IPv4 and IPv6 addresses. They can use either IPv4 or IPv6 if supported by the remote end, and the decision is made based on which address family is returned from DNS lookup for a particular domain. But for that to work, we need support on multiple places. So if you look at, take a look at this picture, on the left side we have some home network with some network devices like mobile phone, laptops in our home, and on the right side we have some service provider. So first of all, if the right side is some Kubernetes cluster which is providing some service, that itself needs to have IPv6 or DualStack support. Then, of course, the ISP, the internet service provider that we use, needs to support both IPv4 and IPv6. And the CPE device, the device that the internet provider gave us to interconnect ISP network with the home network, needs to support it as well. And the home part of that configuration needs to be DualStack enabled as well. So all of this needs to work in order to have DualStack connectivity end-to-end. And why I'm talking about IPv6? The reason is that the IPv6 adoption is increasing. This graph shows the percentage of users that access Google services over IPv6 worldwide. And as you can see, we are approaching 40% of IPv6 adoption. So almost 40% of internet users already use IPv6 to connect to Google services. This picture shows how it looks like on individual countries basis. And if you want, you can make a quick guess in your head what country would be winning here. I'll give you 3 seconds, 1, 2, 3, and the winner is France. So in France, already over 70% of Google traffic or Google users traffic goes to Google via IPv6. And if you want to make another guess, I'll give you 3 more seconds and make your guess what would be the numbers for Czech Republic and Slovakia. 1, 2, 3. It's not that great. So in Czech Republic, it's about 24%, and in Slovakia, we are actually below 10%. So please, Slovak ISPs, if you hear me, please make something with that. Okay, what can we do to enable IPv6 in Kubernetes? IPv6 only Kubernetes clusters were possible since Kubernetes 1.9, so pretty early actually. But IPv6 only use case is pretty limited. I would say focus on specific use cases. Maybe if you want to run something like 5G core network on Kubernetes, then probably you would do it in IPv6 only Kubernetes cluster. But for general application use cases, you would probably want to serve both IPv6 and IPv4 clients. And that's exactly what DualStack Kubernetes clusters allow us. DualStack Kubernetes is a feature which is generally available in Kubernetes since the version 1.23. And if DualStack is enabled in your Kubernetes cluster, then every pod has an IP address from each address family, so both IPv4 and IPv6 address, which is actually the role of the CNI. And Kubernetes services can be declared either a single stack, which is default, or dual stack. You'll see in more detail in a second. In theory, each pod in your Kubernetes cluster can have a public IPv6 address, which also means that you may need more firewall rules in your cluster or in your setup. And unfortunately, in Kubernetes, we have not yet avoided network address translation. Even if we use IPv6, the service load balancing is still based on network address translation at the moment. There is some work, or there's already some people thinking about how we could address that, but at the moment, each IPv6 or dual stack service would get assigned some virtual IPv6 address, which would be netted when the traffic goes to the backend pods. But as you may already know, in case that you are using Cilium CNI, a lot of network address translation can be avoided thanks to eBPF, which is actually the case for both IPv4 and IPv6. So you may take a look at that. Okay, now how you can enable DualStack in your Kubernetes cluster. This slide shows how you can do it the hard way. Of course, in case you are using some smart Kubernetes platform, which allows you to do it by a single click, that's possible for some platforms. But in general, your worker nodes need to have IPv4 and IPv6 addresses, both, for which you may need some support from your cloud provider. And then you need to enable it on 4 places in the control plane. So on Kube API server, Kube controller manager, Kube proxy, and kubelet. You need to configure both IPv4 and IPv6 cluster IP ranges and pod IP ranges. And And last but not least, you also need to configure your CNI to provide or work with both IPv4 and IPv6. In case of Cilium, you can do it quite easily in the Helm chart. You just set IPv6 enabled to true. IPv4 is enabled by default, so just by doing that, you can enable DualStack. Once DualStack is enabled in your cluster, if you describe your nodes, you would see that every single node in your cluster should have both IPv4 and IPv6 address. If you describe the pods, you would see on the first look that the pod looks like it would have only single IP address, but in fact, in the status of the pod, you would see both IPv4 and IPv6 address. And similarly for services, if you request a DualStack service, you would see that the service has both IPv4 and IPv6 address. Actually, since Kubernetes 1.21, each service spec has two new fields that you might have already seen. So there is spec IP family policy, through which you can define whether a service should be single stack or dual stack. Single stack is default, and in case of dual stack, you have two options: prefer dual stack or require dual stack. It works the same way, just require dual stack would give you an error in case that dual stack is not supported in the cluster. And another field is spec IP families, through which you can define which IP family you want to have for that service. So in case of single stack, you can define either IPv4 or IPv6. And in case of dual stack, you can actually define the order of IP families that you would like to use. It's not that important. The order is not that important, as at the end of the day, it still works the same way. But the order would give you a difference if you describe the service or get the service through the CLI. You'll see in a moment. So on the example on the right side, I have a service which is defined as prefer dual stack. So this one requests dual stack if it's available in the cluster, but would not fail if dual stack is not available in the cluster. And in the IP families, I specified the list IPv6 and IPv4, meaning that primarily the service would look like it has IPv6 service address, but it would also support IPv4. This is just an example in case that you opt for not enabling dual stack in your cluster. You can still leave your cluster on single stack and use something like Cilium NAT46, NAT64 gateway for doing the translation for you for all the ingress or egress traffic. So this is a feature that is available in Cilium since release 1.13. You can take a look at the release notes if you are interested in more details. But essentially what it does, it allows you to have a single stack cluster and have a NAT gateway in front of it, which would allow you to also serve the traffic for the other address family. Okay, and now I will talk about about the support of DualStack across some different cloud providers. I'll go through some major ones, then smaller ones, and some on-prem platforms. So, in my humble opinion, AWS is leading here and provides best IPv6 and DualStack support. In AWS, each VPC can get its own /56 public IPv6 subnet. You can bring your own IPv6 subnet if you want, and each VM can get any number of IPv6 addresses. Just if you are using AWS, you need to pay attention on which cloud controller manager you are using, because the AWS load balancer controller supports DualStack, but the standard AWS CCM does not. In case of Microsoft Azure, the DualStack or IPv6 support is a bit different, I would say, because the platform would give you only private IPv6 address range for addressing your nodes and networks. And you would need to request public IPv6 for VMs on per VM basis, and that VM would be that IP would be like virtual IP address that would be network address translated whenever the traffic is reaching your VM. And DualStack load balancer services are not yet supported in Azure Cloud Control Manager. So in case of this platform, it's not yet there, but it's in progress, and I think it should be delivered in Kubernetes 1.28. In case of Google Cloud, there is pretty good DualStack support for VPCs and for VMs, but DualStack load balancer services are not yet supported. Smaller cloud providers, for example, Hetzner has very good IPv6 and DualStack support, including load balancer services, so there everything works fine. In Equinix, pretty good IPv6 support, but not yet support for load balancer services. Similarly for DigitalOcean, pretty good IPv6 support on the node level, but not yet for load balancer services. And now private cloud and on-prem platforms. So for OpenStack, OpenStack in general has great IPv6 support in OpenStack itself, but there is the support in Kubernetes Cloud Controller Manager is limited. And even this limited support, actually, I contributed myself when I saw that it's pretty low-hanging fruit. The limitation is that your service can be either IPv4 or IPv6, not really DualStack at the moment. In case of bare metal platforms or other on-premises platforms, of course, DualStack and IPv6 needs to be supported in the underlying network. And for load balancer services, you can use, for example, MetalB, which supports DualStack in both BGP or Layer 2 mode. Or you can use Cilium load balancer IP address management support. In this one, we are supporting DualStack announcement via BGP. Okay, so to summarize this, I think IPv6 is a necessity due to IPv4 address exhaustion, but also brings many other features. The adoption is increasing, especially in some countries. Most of the internet traffic is already served via IPv6. DualStack can be used for smooth transition to IPv6, so we do not have to stop using IPv4 at a single moment, but we can do both for some period of time. In core Kubernetes, Kubernetes upstream, DualStack is very well supported since Kubernetes 1.23. When it comes to cloud providers, at the node level, the IPv6 support is available at most cloud providers. But the support for external IPv6 load balancing is not that well at the moment. But on many platforms, it is already a work in progress and should be available soon. And while it is not available, you can still use node port to expose IPv6 services in the meantime, or DualStack services in the meantime. Okay, that's for the theory, and now I would like to show you some very short demo. The demo that you can actually do yourself at any time. It is based on a kind cluster that is defined, as you can see on the left side of this slide. So it's a standard kind cluster where I set networking IP family dual. And I also disabled default CNI, as I'll be using Cilium in this cluster. And I also disabled kube-proxy in this cluster, as I'll be using kube-proxy replacement of Cilium. And on the right side, you can see how I installed Cilium into that cluster. That's pretty much standard thing, I would say. But what's marked with orange is IPv4 enabled equals true and IPv6 enabled equals true. That's how we enable DualStack on Cilium. Okay, now let me go to my console. So this is our cluster. As you can see, it is running Cilium. If you pay attention, you may see that kubeproxy is not running there, as I have disabled it. We are using kubeproxy replacement of Cilium. And in the default network namespace, I have two NGINX pods, which look like they have only IPv4 address from this output. But if we describe the pods and explore the output a little bit in depth, we can see that each pod actually has two IP addresses, one IPv4 and one IPv6. Similarly, if I describe the nodes, or first I would get nodes. I have three nodes in my cluster. They look like they have only IPv4 internal IP, but if I describe them, you may see that the nodes actually have both IPv4 and IPv6 addresses. And if we explore the described node output a little bit more, you would also see that we have two different pod siders allocated for each node. One is for IPv4 address family, and the other one is for IPv6 address family. So the pods on this node would be assigned this IPv4 addresses from this range and IPv6 addresses from this range. Okay, now I would run a new pod in my cluster. Just running a shell in the pod. And if we take a look at the IP addresses or interfaces in this pod, you would see that on the ETH0 interface, we have one IPv4 address, and we do have one IPv6 address. This one is the, with the global scope, is the one that was allocated from the pod sider of the node. There is one more IPv6 address, which is a special IPv6 address that has just link local scope. Every IPv6 enabled device has this link local scoped IPv6 address, which is auto allocated. And I don't know if I still can access, if I still can see the output of some pods. Okay, let me maybe go back. So let me describe some pod again. As you can see, this pod had two IP addresses, and we can try whether we can ping the pod through both IPv4 and IPv6. So I'll copy first the IPv6 address. I'll go into my temporary pod, and we can try curl into IPv4 address, and that is working. And we can also try curl to the IPv6 address of the pod. And that is working as well. But what's more interesting is the services. So if I describe the services in my cluster, I have already deployed them, and I deployed various different flavors of DualStack services. And as you can see on this output, some look like IPv4 and some of them look like IPv6. But I will describe them and I'll show exactly how it works. So I deployed one service, which is DualStack with preference IPv4 first and IPv6 next. And you can see that it has two cluster IPs allocated. First is IPv4 and the second one is IPv6. I have kind of the same DualStack service, but with different order of address families. First is IPv6, and the second one is IPv4. Then I have a single stack service, which is IPv4 only, and has only IPv4 cluster IP. And then I have an IPv6 only service, which has IP families IPv6 only, and has IPv6 address family. Let's focus on one of them. Let's say this nginx DualStack v4. So that's a DualStack service. I will go back into my pod. Hopefully it will work. Internet, maybe. But what I wanted to show is that if it worked, if I did NS lookup to that service name, you would see that I would get both IPv4 and IPv6 address in the replies. Actually, to my NS lookup request, the pod would send both A and for a DNS request, and I would get response for both of them. So at this point, I can again use either one or the other. So I'll just try the IPv6 one. And, sorry. That works. And the last thing, I'll try IPv4 one, and that should also work. And that's it for the demo. If you want to play with DualStack, you can do it yourself. At Isoval and Com Labs, we have several handful labs that you can use to explore networking with Cilium yourself. This particular link would guide you to IPv6 networking and observability lab that you can run in your browser and play around with DualStack. Thank you.
Thank you very much. We have some questions, and we have still time to answer them. So first one, when do you expect that the majority of the internet will primarily use IPv6? And there's a second question in that question. Can there be another protocol in the meantime?
I don't think there will be another protocol other than IPv6. I think that one suits well for the needs that we have. As I already showed you, even complex stuff like segment routing is already possible with IPv6 because it is extendable. When do I expect? I really don't know. As you saw already, France is already primarily on IPv6. So it is really, the answer would be specific to individual countries.
And speaking of individual countries, what's the current situation with Slovak internet providers? Is there an IPv6 option?
Yeah, as I've shown on one of the pictures, so in Slovakia, about 10% of internet users are using IPv6 to connect to Google services. So some of them are already supporting it, but the majority not yet.
Perfect. And the last question, doesn't the additional processing power required for managing large number of firewall rules outweigh the saved processing power required for NAT?
Yeah, I think NAT has definitely more complex processing, or requires definitely more complex processing than access lists. Because NAT needs to store the state of each individual session, whereas for packet filtering, you pretty much just have a list of static rules. So,
thank you very much. That concludes our presentation. We will continue in 5 minutes, and we can thank the speaker with an applause.
Thank you.